Okay, so we are the public key cryptography group, and for most of you, you'll be asking, what is public key cryptography? Now, in the modern day, we have everything from online banking to private messages online, and one of the key problems with this is that we need a way to keep it secure. I mean, you don't want your best friend seeing the message to your crush, do you? So, public key cryptography, how does it work? Well, cryptography, to start off with, is a way of enciphering text or data in any way possible so that anyone who interprets this as it is sent cannot read it in clear text. So it's basically a way of adding another step to access this data. Now, the most basic form of this, or, well, one of the most known forms of this, was used by the Romans, hence its name, the Caesar shift. Now, the way that the Caesar shift works is that the alphabet is presented alongside the same alphabet. So for us, it's the 26 letters. It is then shifted by a certain number along so that the plain text alphabet correlates with another alphabet. So for example, with a shift of 23, the word hello goes to evil, as shown. This is because of the way that the alphabet's shifted.
So one main problem with the Caesar shift is that, with using it nowadays, is that we tend to do quite a lot of stuff over the internet, and while it's fine if you're just sending a messenger over to the next camp, you can't really do that when you're sending a message from America to China. So the main problem with the Caesar shift is that before you send a message, you need to before send the key along. So say that Alex wished to send a message to Reese, but he did not want Jason to see it. So he could encode his message, both would receive it. Jason would not know what it was saying, but unfortunately, because he encoded it, neither would Reese. So he has to also send the key beforehand. But since Jason will have the key and the message, well, okay, yeah, so Reese could decode the message, but unfortunately, so can Jason. So there's a bit of a problem there. So this is where public key cryptography comes in. So the way this works is that Alex would send a message to Reese saying something like, I'd like to send you a message. And then Reese would do some maths and would calculate two different numbers, which would essentially be like an open padlock and a key. He would send the open padlock back to Alex. This is just some numbers, so nothing to do with the message, so Jason can't really do anything with it. Alex will use that to encode his message. But now that he's used it to encode the message, he does not have anything to decode it, so he sends it back. Again, Jason can't do anything with it because he doesn't have the key, but then Reese, because he does have the key, because he made it, can then use that to decode the message.
So, in the modern day world, RSA is incredibly useful for banks and online shopping websites. This is because it enables them to perform secure transactions completely over the internet. But before public key cryptography was implemented, the encryption keys had to be physically sent for the transaction to be secure. It helps that it's not owned by any private company, so anyone can use it, and it can encrypt, decrypt, and verify, all using the same function, so it's become a de facto standard.
So the public key is a number which is a product of two prime numbers. So the way to calculate the private key, you need to get those two prime numbers, do some maths, and then you get the private key. So in theory, in order to break RSA, you need to factorise the number, which is the product of two prime numbers, into its own two prime numbers. So as a recap, prime numbers are numbers greater than 1, which have two divisors, itself and 1. And factorisation is the process of splitting numbers, which when multiplied gives the original number. So here are some examples of prime factorisation. So in your head, no shouting out. What's the prime factorisation of 21? It's quite easy. It's just 3 and 7. You can do that like 5 seconds. So now 91 is a bit harder, but after like 10 seconds, you can say, oh, it's 13 and 7. But then try 54,953. It's a bit hard, unless you really want to try it, but since I'm a math genius, I know it's 379. So as you can see, as the numbers gets bigger, it takes more time to factorise the numbers. And the same principle applies to computers. So here is a 1024-bit number here. It's pretty big, 309 digits. And for computers, this is a nightmare, as it can take thousands of years to factorize. But it takes a computer a second or less to produce that number. So here I made a program, which is a brute force method of trying to factorize the number. So it basically loops through the numbers and checks if one of the numbers is a factor. And once it has the factor, it can then divide that number by the factor to get the other factor. And there are other factorization methods, such as the Fermat's factorizations and others, which are much better than this. This is quite slow. So this is it for modern computers, but we're just going to talk about quantum computers, which can do a quicker job.
Okay, so in recent months, well actually since we started this project, RSA has been decrypted by quantum computers. Now for a lot of people this could cause panic, you know, this is our bank data, our messages, everything, which could be decrypted. The one issue with that is that the only people that have this is IBM, who have spent multiples upon multiples of millions of pounds to get these quantum computers, simply to take 2 months to decode a single bit of information. So for now, I feel like our information might be safe. So one of the things is due to this concern over in the future, could quantum computers or powerful computers be accessible to the public? Currently, cryptographers and pure mathematicians at universities like Cambridge and Oxford are working on a way to encrypt our data a lot safer. For example, if a computer can physically do it, like RSA, then it's possible to do it. They're doing more of a approach, which means that no one knows how to decode it to make it more safe. So that is pretty much the general consent of what we've done. So many thank you to Dr. Gihan Marasinger of Exeter University for presenting us with this problem and for the help that he gave towards it.